What's up, guys? Welcome back. Today we're learning about solids, liquids, and gases.
Cool. Smash that like button. Subscribe. Huge shout out to Zeke, who was like the one Patreon viewer last week. Cool. Here we go. Today we are starting chapter 14. I don't like that up here. We're gonna move it down there. We're gonna start chapter 14 today. So, in chapter 14, we are only looking at 3 ideas. Now, remember, we're making the transition from doing the physics and the kinematics, which is just the physics of movement, back to chemistry. So, introductory chemistry is what we're going to see in here, but inevitably, there's going to be an overlap with physics a lot of the time. It's going to happen. Be prepared for it. Like last chapter, I just want to stress the importance. If I say something that doesn't click, you don't understand, what do? Call me out, yeah, for sure. Please ask questions. The more talking you do, the less I have to do, which I love. So, chapter 14, we are looking at solids, liquids, and gases. Okay, so we're going through here. Solids, liquids, gases. There is a 4th state, which will be discussed at least briefly, but let's check it out. 14.1 is our first section. So module 14, section 1, I think is the language I use. But we're going to be talking about 2 things and connecting them. So matter, first of all, matter and thermal energy. All right. Matter and thermal energy is our focus. It's been a while. What's matter? Stuff that makes us up. Just people?
No, everything.
Everything. Light? Is light matter? Are you sure?
No.
Okay, I'm going to make a claim. I want you guys to see. I don't know how much you know about it. What? No, it's a true statement, but I want to know. Weird. This statement is false. Is that true or is that false?
This statement is false. That means it's true.
That's true.
But that's a true statement, then the statement's false, which means it's now false. And Interesting. Not our focus. That is a paradox. You can't solve that one. But here's what I do know. Light is not matter. Light is not matter. Why? Talk it out. There's something more fundamental that didn't get hit when I think Sunny answered it.
It's not physical.
Light is physical.
Kind of not. Talk it out. Why is light not matter? Weird.
It's like a rainbow.
All right. So coming back together real quick. Can I step on a scale and weigh me? Okay, it's unbelievably small, but could I put a single proton on a scale and weigh it? Yes, it has weight or mass to it. Okay, a piece of light or a single particle of light or a wave, depending on how you're thinking about it, it's called a photon. There is no mass. They are massless. It's pure energy is all it is. Okay, so as we're looking at this, when we talk about matter, we're talking about the physical stuff that takes up space. So it has to occupy some region in, 3-dimensional space, but it also has to have some mass or weight and stuff inside. You need to be able to weigh it given the right technology. So that's matter. We talked about thermal energy a bit as well. When you see the word thermal, what does it make you think of? Heat, temperature, good. I'm fine with that. So to start right in, we have to agree on what we mean by matter and how it works. So our first main topic today is what's called kinetic theory. Kinetic theory. And I'm going to say kinetic theory of particles. Okay, this is a really fancy sounding thing, but there's only a few fundamental pieces that I think we can all agree on. I hope. Now, all that kinetic theory tells us, and I'm going to write way less than I'm speaking. Everything that we've ever dealt with that's matter is made up of small particles. Particles that have energy, and they always do what? If we look back to the thermal section. They're always moving at least a little bit, right? Even when we went all the way down to 0 Kelvin or absolute 0, we saw that they were still moving just a little tiny bit. So In shorter version of that, instead of saying, hey, everything's made of matter that are little particles that are constantly moving and interacting, we're going to briefly hit this a different way. We're just going to say that this is an explanation of how particles behave. An explanation of how particles behave. Okay, that's it. Now, I am made of particles. You are made of particles. Water is made of particles, and water is the easiest one for us to use in like an example over and over because we have a lot of water on this planet, and we get it in all three states of existence. So, are we starting cold or are we starting hot? Cold seems like a good way to go. So, check it out. If you have really, really cold water, what is it? It is ice. So I'm going to use blue because that seems to make a little bit more sense. Let's look at our first state of matter. I'm not going to write ice. I'm going to write solids. Okay. The solid state. Okay. For this, I like to use the people analogy because I think it makes the most sense. It's easy for us to look at. First and foremost, if you're really cold, is it because you have too much energy or too little? Too little. So we'll just say lowest energy. If you're cold, you are lacking energy. Now, once we have this, right off the bat, we are still made of particles. Are they still moving? So we're going to come back to this one. And I totally get no. The only time we would not have any sort of movement, the only time is if we're at 0 Kelvin. So I'm just going to go to solid here. That's pretty cold. We'll go back to Celsius just a little easier. Negative 130. Pretty chilly. They're still buzzing. However, it's almost like they're kind of locked in place. As I see this, if we pick any single one, here it is. It's moving around all of its neighbors, but is it ever truly leaving? No. So particles still moving, first and foremost, but they move a lot less. So we're going to make that an easier statement. Energy so low, particles only wiggle. Now, depending on the substance, there's a lot of different types of, obviously, substances that we can deal with. When I think of frozen, I think of cold. Do you guys agree with that? Okay, somebody who has a plastic pencil, could we melt it? Like, not physically, I'm not going to melt your pencil, but could we do it? Which means you could turn your pencil into a liquid, right? Which, this is just a weird language thing, but I need to make sure that we all agree on it, and I'll try to stick with it. Is your pencil feel cold right now? No. Not kind of. Is it like freezing cold? But here's the distinction. With water, when we say it's solid, it's frozen. Right? And it's frozen water. If you have a plastic pencil in front of you, is it solid right now? Yeah. Would you agree then, just by language, it's now frozen plastic? Like, its freezing point's just different than water, right? Like this desk right here, there's metal on the side. It's not like freezing cold, but is this frozen? Yeah. This is the solid state of this metal. It has not melted into a liquid yet. It must be frozen solid. It's a weird idea. Do you want to use that language of frozen for stuff that's not as cold as frozen water, or do you just want me to avoid it? Feels okay? All right. Energy so low, particles only wiggle. Now, if we have anything frozen, can you stretch it out nicely? Like, take something in front of you that's not melted. Can you stretch it and change its shape? No. So it depends on it. What are you thinking? So maybe a little tiny bit. I agree. If we made it colder and we just stick to ice, for example. Let's look at solid water. This is going to be the easiest example. Can you stretch water? Especially if it's frozen water. You definitely cannot. When it's frozen water, can you change its shape? Yes. How do you change the shape of frozen water? If I have a block ice cube in front of me and I want it to be the same amount of ice without getting rid of any, like I can't shave it, can I really change the shape of an ice cube? You say yes, how? But you're changing the shape of a liquid at that point. As soon as you melt it, you no longer have a solid ice in front of you, right? So you might be able to, let me rephrase this. If I have a block of ice in front of me and I'm not allowed to melt it, can I make it a sphere of ice? You think so? So a hydraulic press you might be able to use. We're going to work under the assumption that we don't have a hydraulic press in our pocket. These things, solids, definite shape and volume. I'm going to put an asterisk because with enough energy, maybe there's some weird things that happen. I'll tell you, with the TikTok of watching a nice ice sphere get made, you're pressing so hard that you're getting it to melt and it's refreezing itself is what's happening. Like you can cut an ice cube with a piece of wire and we can check that out. However, look at this. Definite shape and volume, super low energy, and then not all the time, but oftentimes, these guys often form into a crystal lattice. Now, that sounds maybe fancy, maybe not, I can't really tell. When we talk about a crystal lattice, it's imagine that we just have these nice, really structured and ordered pieces, just like this, where they're just perfect. They line up, they're stuck together, they're in this nice organized fashion. That is a solid. Lots of different minerals do this naturally. Quartz and all the variants of quartz, diamonds, gemstones, they all do this. Ice also does this. Does metal do this as nice? Depends on the metal, realistically. I heard somebody mention TikTok a few minutes ago. Have you guys seen the bismuth crystals on TikTok?
What color are they?
Iridescent. We're going to do a quick little brain break of the coolest metal that you can buy on the internet. I don't know if it's really the coolest. I think gallium's cooler. But if you've never seen bismuth, it's awesome. I'll tell you, I think everybody in here, anybody know bismuth off the top of your head? So, off of Steven Universe, maybe. I don't know that character, but there's one out on the wall. I bet you guys have all drank bismuth.
Probably.
I bet you've eaten it, you've drank it. I'm actually going to say middle because I don't like it, but middle energy. All right, what I want you guys to do, I want you to consider these three things. The energy, what is its shape and volume, and one of them, is it always the same? Can one change? And then what do you think the particles would look like in a liquid? I'm going to give you a minute. I'm going to come around and be real judgy about how you draw these things in your notes, and then we'll put them up on the board once we're in agreement. Talk it out with your neighbors. These same three ideas, energy level, what do the particles do? What do we know about the shape and volume? And what might it look like if we were to draw it? Cool. I'll give you a minute. So check it out. We have a little bit more energy, which more energy means you're moving a little bit more, right? So if we only wiggle a little bit with solid state, how would you describe how they move here? They wiggle harder, first of all. Wiggle more. And I'm going to even add more beyond this. Is it possible that if I have a cup of water, and I'll just draw it, you don't have to draw the cup. Let's say I have a cup of water sitting here. And then there's a particle of water up here because it's full. If I wait enough time, is it possible that this particle eventually winds up down here? Yeah, would that happen in a solid? So they wiggle more, and I'm just going to say maybe past each other. They're not stuck in place. Okay. Now, this next one, if you've ever jumped from somewhere really high, you have seen this and felt this. If we want to use like a car jack, for example, we're trying to lift up a car. What's inside of that fancy jack that you have? So that's a tough question. Anybody know?
The jack?
Yeah, what's inside of a jack?
Isn't it like clips and like gears?
So it's not gears and stuff. A ratchet uses gears and leverage from the length of your lever arm. With this, it's just hydraulic fluid, which is just really dense liquid. Yep, it's hydraulic fluid. You could use water, and people do use water, in fact. As we're looking at this, if I have a cup of water, and I'll put that same cup back up here.
Is that the blue stuff?
It's usually like really dark. Let's say I have a cup of water, and it's in here. And then I put a hydraulic press on top. Have you guys all seen the TikTok videos where they do this? Okay, if this thing pushes down, what's going to happen? Will the water compress?
No.
Not at all. Which means you cannot change the volume of a liquid. You cannot do it. Anybody ever jump from really high up in the air? Okay, if you jump from high enough and you land in water, it essentially feels like you're landing where?
Concrete.
On the ground, on concrete, because liquid doesn't compress. It is definite volume. Could the shape change though?
I thought it depended on how you are, like how you.
Yeah.
Not really. You jump from high enough, you're not going to live even if you land in water. Really.
Minecraft lied to us.
Nope. You'll first break your fingers and then the rest of your bones will break after that because you're slamming into a liquid that does not compress. So we'll look at this. We'll say definite volume. It can't take up more or less space. Definite volume. But not shape. I can change the shape of a liquid. It can fit in this cup. It could fit in a cup where it's straight vertical. It can fit in either. The same volume of water is going to be present in both cases. All right, the last one. If we wanted to look at how this goes, it's hard to draw it without being able to see the animation. But if I draw some particles here, they might be moving, and I'm just going to indicate with some arrows. Maybe they're moving a little bit, but notice they're still contained within a container. They wiggle past each other, but they don't wiggle out of the container. All right. We hit what do the particles do? What about the volume and the shape? And a little bit of the picture of what it looks like. They can wiggle harder past each other. Cool. With 2 rounds done, are you guys... No, we're going to try it. I want you to try to do the third. We have solid state. We have liquid state. What's the last? Gas or gaseous. Gaseous, if you will. The gaseous state. High energy. I want you guys to discuss with your neighbors these same 3 ideas. How do they wiggle? What about the volume and the shape? And what would they look like in a container? And I'm going to call on 3 people to help me fill this out. Talk it out. Get loud. Get crazy on topic, though. First off, what do the particles do? Who haven't I called on? Chelsea. How hard? Okay, they wiggle a lot. So we'll say wiggle a lot. Now, even if you're looking at water, for example, and the water starts wiggling enough, does it leave the pan?
No.
Are you sure?
It just flashes.
Check it out. You ever boiled water?
Yeah.
Okay. Do you see water in the gas state leaving your pan? Because it wiggles so fast and so violently that it says, peace out, water. I'm not sticking with you anymore. And it rises. Right? Steam does this. So we'll say wiggles a lot. May leave. And by that I mean the group that it's with. Cool. You can boil water. We've all seen it. I think you can probably do it. Okay, right now, can you imagine that I'm an enclosed shape here and I'm holding some amount of air? Can I do it like this and change its shape and now it holds this much air? Could I do it like this? And it's still the same amount of air. Can I change its shape? Absolutely, we can change the shape of a gas. It's just whatever's holding it, right? So no definite shape. Or volume. I can take however much air is in here and I can squeeze it down and have the same amount of air in a smaller area and the same amount of air in a smaller area. This happens all the time. If you've ever aired up your tires using a little tank, this is how it's done. They store high pressure air, which is a lot of air in a little space. It wants to leave and it flows into whatever you're filling up. Okay, what about the particles? The picture of it. So we have some particles here. And first off, what's different about this picture compared to the ones above? They're separated and they're spread out, right? Some of them are leaving. I'm okay with that. Just like you guys naturally do. If it's real hot, oh, I missed your foot. If it's real hot out and you're with like a group of 10 people, are you guys going to huddle up close?
No.
Not if it's really hot. That'd be miserable and sweaty and uncomfortable. If it was really cold, would you?
Yes.
Particles do the same thing. Really important distinction. Do particles have feelings?
No.
Not to my knowledge. I don't think so. They don't. I mean, I don't know that. I'm a bunch of particles having thoughts and feelings right now, so maybe they do. But in general, I don't think so. Cool. All right. Watch me whip. Later, guys.
You know,